PhD student, Ameen Zerrad. He's from Drake Lab. He's likes very much quantum optics and many other theoretical topics associated with quantum physics. For a while, he had a fellowship at Princeton University on astrophysics, right?
Yeah, internship. Yes.
Internship, right. So today he will give a talk. Please, floor is yours.
Thank you, Chris. Yeah, guys. So I guess as he pointed out, I'm Ameen Zerrad. Obviously, I'm from Drake Lab. My advisor is Terry Drake. I do enjoy theory stuff, but today's talk will be more so on some experimental stuff. So I'm sorry to all my theoreticians here. There's another person who wants to join, I guess. Good. Awesome. I think he already got letter. So
Yeah, like there was somebody, right? In the waiting. I don't see anybody in the waiting room.
That was Philip, but I already let him in.
Okay, that's good. Okay.
So I'll be under the assumption everyone here is at least the graduate level. So let's just begin. So I'll be talking to you guys about broadband light generation and nonlinear silicon nitride microresonators. So begin. And so this is the overview slide. I'm sorry, I kind of like to move around a bit. But anyway, so there are already existing platforms that are used to generate broadband light. That includes, your OPO or your parametric oscillator, which can be used to sort of coherently connect some pump signal to some disparate spectral signals known as the signal and idler. This is useful for producing laser sources where it's just not already available. Or you have an optical frequency cone, which is essentially in the time domain a set of solitary pulses. And if you take the Fourier transform and take the frequency domain, you get a sort of equidistant grid of frequency modes that form the shape of a cone. It's very useful for precision spectroscopy, metrology, and also, as you can see here by this graph, it sort of gives you a good link between optical frequencies and microwave frequencies. So for example, you could take an optical frequency and divide it down to microwave frequencies. And as you guys may already know, optical frequencies, you can't measure those directly on a photodetector, but you can with microwave frequencies. So this could be useful for, sort of trying to increase the precision of atomic clocks that usually leverage microwave transitions. So rather using microwave transitions, you could use optical transitions. But, with optical transitions, you get optical frequencies out. Can't read those on photodetectors. But hey, you got your frequency cone, which can sort of, take your optical frequency and divide it down to microwave frequencies, such that you can read them onto a photodetector. And they're great. They've been around for years. So what I show you here is a sort of tabletop laser frequency cone. And you can kind of see the problem with it already, especially to my theoreticians here. It's very complicated. There's a lot of sort of ingredients, so to speak. You need a lot of optics here. You need laser light. It's expensive and it's pretty large, right? So it can be pretty difficult to sort of use a laser frequency cone. A laser frequency cone has all these sort of applications. It could be used for a lot of different sort of fields in physics to leverage this high precision, bulky sort of tabletop scale, its complexity. And so how do we address that problem? Well, the way you can sort of address this problem is with PICs, which are photonic integrated circuits that sort of, modify, transport, and generate light onto a chip scale. And these PICs can sort of take your bulky tabletop experiment and miniaturize it just to one chip. And there's many advantages with that. For one, you can meet your sort of demands at eye level, so to speak. You have these people who want to leverage the precision of frequency cones, but they don't want a tabletop experiment. Want to just buy a chip. Not only that, it's cost effective for mass production. You can integrate this with silicon microelectronics. And, the lower you go with nonlinearities, the lower your volume scales, the lower your power consumption is, the more efficient these nonlinear processes that are leveraged to, generate something like a frequency cone will be. So our goal really is to optimize the design of silicon nitride microresonators for broadband light generation. So I'll start with my first sort of talking point here. It's the Kerr effect and microresonators for light generation. So microresonators, this is something that's been around for a very long time. They come in a lot of different, flavors, shapes, and sizes, if you will. So you have your microsphere, you have your microtoroid, you have your microring, you have your micropillar, you have your microdisc. Before I talk about the materials, let's just note here that they all sort of have this convex geometry in common. And that's not for no reason, so to speak. So this geometry really that you have here, a convex geometry like this works as almost like a acoustic whispering gallery. So this is an example of like St. Paul's Cathedral, where if a listener was here and a talker was here, if they, start whispering, you could actually hear it on the other side of the room. And this is because these convex geometries sort of confine sound waves very tightly by almost total internal reflection. So what you can do with sound waves, we said, well, why don't we try this with light waves? So that's the idea. Is what we do is we deal with microring resonators. They can be many different materials, but we leverage silicon nitride because we're interested in four-wave mixing. We want high quality factors so that we can build up a lot of power in the cavity. These are, you're trying to generate light through nonlinear processes. So nonlinear processes require a lot of light. I'm going to talk more about that later. You want a small modal volume because the intensity is inversely proportional to the area. So the smaller the volume, the more intensity you can build up. When you have this sort of microresonate, this microring resonator, you have good controllable dispersion, which will be very important when you're all focused on that later in my talk. And this sort of microring resonator can be integrated with other on-chip electronics or photonics. Okay. So like I said, our business is in silicon nitride Kerr microresonators. So that has ring radii between 23 and 230 microns. So with that ring radius, your light travels anywhere from 1 to 10 picoseconds per round trip in the ring. You got quality factors between 1 and 5 million. And I know quality factor is a bit of a jargony term, but it'll matter later in the talk, and I'll kind of describe it better later. But just take it with a grain of salt. You have your ring height, which is 670 nanometers for our devices that I'll be talking about in this talk. Ring width is anywhere between 650 and 790 nanometers. And we have them cladded in silicon. You can mess around with cladding to get better optical confinement, but we chose silicon cladding here. And here I'm just essentially showing you a cross section of this like face on of a ring resonator. I don't know if you guys can see me well, so sorry. Maybe I can sort of.
You can turn camera out there.
Oh, really?
Yeah. Is there?
Yeah, that kind of works. Oh, shit. So this is your microring resonator here. Right here, this might be confusing to you guys. I just want to point this out because you're just saying, oh, Ameen, this is a microring, but what's with this rectangle? So this is a sort of bus waveguide that you use to inject the light that you want to go into your microring resonator and interact with something like that. Thanks, Chris. Okay. Next slide. So how do we generate broadband light with these microresonators? Well, we leverage the Kerr effect. To all you guys who have PTSD from electrodynamics, this will look very familiar. This is your polarization expansion. And what we're interested in is this third order nonlinearity term, which contains the Kerr effect. What the Kerr effect basically is it means that your index of refraction now becomes a function of intensity. And so when you have a Kerr type material, when you interact with it with light, you can sort of generate four-wave mixing via the Kerr effect. So we can sort of look at this in a two-level system almost, in the sense that, pump photons from the field that you're sending to your Kerr medium are absorbed by this medium. And because of the Kerr effect, what happens is four-wave mixing, which results in the generation of spectrally disparate signal and Eidler's photons. So anytime you have something like this, you have to play by the rules in the sense that you must conserve energy and momentum. So to conserve energy, that imposes a sort of frequency matching conditions. So this is your frequency matching condition to conserve energy. And also to conserve momentum, you have to have these sort of phase matching conditions. And so this is why sort of control of the dispersion is very important with such systems, because through careful choice in the design of the microresonator, or rather control of the dispersion, you can satisfy these phase and frequency matching conditions such that your device can support full wave mixing. And so here I just wanted to point out also, as you can see, is the optical nonlinearity or the optical susceptibility, the third order one. It scales with intensity. So this means that, this is why it's important that you have this small motor volume. You're building up a lot of intensity so you efficiently have four-wave mixing. You also want high quality factors such that, you don't have much loss with the light sort of traveling through the ring. So you don't lose light. You have as much intensity as you can. You can get it as efficient four-wave mixing as you can. Speed walk, speed walk, speed walk. Anyways, so next I'll be talking to you about microresonators designed for spectral translation. Bit of a jargony term, but I'll talk it out for you guys. So what are microrings designed for spectral translation? Quantum emitters, such as your 2D layer membranes, quantum dots. No, sorry, it's okay.
Which was this one?
This one. You're all right. You're all right. No worries. I'm sure a lot of you guys here know much better about these sources than I do. I'm a microresonator guy, but I know that these emissions can be used to sort of quickly and securely transmit information. Moreover, anytime you put quantum in a grant, you're going to get money. So everybody loves quantum now, which is great. I do too. But anyway, so here's the challenge we face with having these sort of quantum emissions on a chip, and it's the range at which they emit. Typically, they emit in a wavelength of 500 to 800 nanometers. Of course, there's some efforts to have new quantum emitters that sort of emit more so towards the telecom, but in bulk, usually they emit in this range. So what's the problem with that? Well, you guys are most likely familiar with Rayleigh scatter, which is the reason why sort of, as the sun goes down, the sky goes from blue to red. And what that essentially means is that blue light is more likely to partake in scattering processes than red light. So this sort of bluer wavelength relative to something like 1.2 micron or 1,000 nanometers or 1,200 nanometers will be much more lossy just because it's, at a shorter wavelength. Moreover, when you have something like a quantum emission, things like scattering processes can result in a loss of information, can lead to decoherence. It can essentially make it so you might as well not do it at all. So that's the challenge we face. So in an ideal world, it'd be nice if we could have these quantum emitters just emit at in the telecom wavelength, where silicon nitride's well tested for this. Most of your communication all is in the telecom right now. So rather than tackling, new quantum emitters, what we're trying to do is sort of use a coherent bridge to take this quantum emitter at 500 to 800 nanometers and sort of spectrally translate it to 1.2, into the telecom, 1.2 microns, into the telecom wavelength regime. So if we can sort of take these, the information, the phase and frequency information associated with these quantum emitters, and sort of pass them on like a track star passing a baton to the telecom wavelength, where it's much less lossy, you're less likely to lose information. This would be great. This would be a pathway to sort of putting quantum emitters onto a chip, or one way of doing it. This is the way we propose it. So, okay, so you told me this is what you want to do. How are you going to do it? Well, there's the optical parametric oscillator, which I noted, it can take pump photons and coherently connect them to spectrally disparate photons known as the signal and islet photons, where, again, we can look at this in a two-level system, which, again, this is the four-wave mixing two-level system I showed you guys earlier. So that's the way we're going to generate a parametric oscillator, is via four-wave mixing. Okay, so pump photons from the field are absorbed, and then Eidler and signal photons are emitted. And so in the frequency domain, essentially, you have your pump here, you have your signal photons here, you have your Eidler photons here. And so how do you do this? Well, you have to do it via four-wave mixing, but again, you have to conserve energy and momentum, and that's going to matter later. So what we propose is sort of seeded OPO in the sense that we take a weak signal, let's say from a quantum emitter that's anywhere between 500 to 800 nanometers, ideally. And we allow it to sort of interact with the carrier-type medium that's, generating our parametric oscillation. And this weak signal will sort of write its phase and frequency matching, its phase and frequency information onto the medium. And we use an intense pump to sort of drive the process, such that we can take the signal photons and connect them to the either photons through our phase and frequency matching conditions. As you can see here, if you want to conserve energy, you want to conserve momentum, then you have these frequency matching conditions, but you also have these phase matching conditions. And this is the beauty of the parametric oscillator, in the sense that it allows you to connect information, frequency information associated with the pump, with the either signal. Similarly, it allows you to connect phase information with the pump to the either signal. So what it sort of allows us to do is take the information associated with the signal and pass it on to the either photons, which are essentially at anywhere between 1,000 nanometers to 1.2 microns, or 1,000 nanometers to 100 nanometers. And these signal photons are anywhere between 500 and 800 nanometers. So that's what we're proposing. How would you do it? So you have your weak signal, your weakly intense signal, which is blue of the pump. And you have your intense pump that's green of the signal, which kind of makes sense, or red of the signal, if you will. So what you're going to do is sort of send in some intense pump light in your seed signal and allow that to couple into the microring resonator. This microring resonator is a silicon nitride material. As I told you guys before, when you have light interacting with a carrier type material, such as silicon nitride, you get processes such as four-way mixing. That's very interesting for us because four-way mixing is what we propose for parametric oscillation. So what happens is that the pump light and signal, they propagate, or they travel through this ring, they interact with the carrier type material, and then it results in the generation of signal on either side bands, which get outcoupled by the same waveguide. And so what this allows us to do is sort of seed microrings with a near visible emission and a pump that will coherently connect light at longer wavelengths biased by a spectral translation. So again, the end game here is to take whatever phase and frequency information is associated with the signal photon and pass it to the telecom either photon, so we can avoid high losses in our integrated circuits, our photonic integrated circuits.
Excuse me, how far is this ring from this line that you have closed ring and there's a line? What's the typical distance?
You're talking about from here?
Yeah.
So it depends really. Anywhere in these devices, I'd say anywhere between 400 nanometers, let's say 700 nanometers.
And what's the size? What's the diameter of ring and what's the diameter of this cable above?
So the ring width is anywhere between, so if I were to draw a cross section for you. So this here.
So you can also direct the computer screen.
Oh, yes.
Obvious the right word as well.
Yeah. I wish you guys are all here. I really like to write on boards. It makes it hard to see, so I'm sorry. Anyway, so this is sort of cross section of your ring resonator. So you have your ring height, which I'll just call RH. You have your ring width, which I'll just call RW. So the ring width is anywhere between 650 790. Your ring height's fixed at 70 nanometers. You can't really change that. And I can tell you why later. But the bus waveguide, we're not so concerned with it matching the cross section of the ring resonator. We fix it at 600 nanometers. The idea really is just to, design the bus waveguide in such a way that it minimizes propagation loss. So you don't want to lose that much light before you get to the resonator. Because if you lost all that light, you might as well not done it at all. And the coupling gap becomes very important for efficient outcoupling, which is another part of my talk later.
I would love to hear the paper reference on this coupling, description of this coupling.
Sure.
That would be nice.
Sure. There is a paper that I'd recommend. Maybe not so much on the coupling, but more so on designing the dispersion. It's by Autonomy, kind of blanking on his name, Autonomy, but the paper is about integrated dispersion. So maybe towards the end, I can show you guys this paper. I don't mind. Yeah. Okay, this is great. So, well, how do we settle on our parameters? Well, we utilize finite element modeling or FEM simulations. So from the FEM simulations, we obtain a refractive index function frequency for silica-cladded devices, fixed silicon nitride layer thickness, or the height of 670 nanometers. And why fix the thickness? The reason why is like, so the way we get them, all our devices on what we call a chiplet, which is like a little microchip. So you have a bunch of microresonators on this chip. So it doesn't matter how things are fabricated. Of course, I'm not an expert in fabrication, unfortunately. You don't have that degree of freedom of varying the ring height. Once you pick a ring height, it's like picking the material. You're set. You can't change it. If you tried to change the ring height from device to device, you would get some fabrication issues. At least that's what the fat guys tell me. Right, and we have our variable ring width here. Oh, also, I should probably point out, this is what I see on console, guys. I think it's actually pretty cool. You guys probably can see it, but I'll still turn it anyway so you can see where I'm pointing. Essentially, what you're looking at here, so this is the cross section of your ring resonator. So this is the ring width. That's the fixed ring height. This is silicon nitride. It's sitting on silica, and it's also cladded in silica. Here, I'm essentially showing you the mode, the fundamental T mode in the waveguide. Where here, this is your electric field in the color wall, And so I'm just showing you a fundamental T mode sampled at about 400 terahertz for a ring radius of 225 microns. We'll speed roll.
Okay, go ahead.
No, sorry. So I'm sorry, guys. Here's the bit of a boring part, but it might be very interesting to you theoreticians here. How does finite element modeling work? This talk was proposed as like a student colloquium. I also used it for my second year talk. So I didn't really know my audience, whether or not they knew finite element modeling or didn't. So I thought this was a good slide to have, just to give you an idea of what is finite element modeling, how does it work? So COMSOL, it's a numerical solver for boundary and initial value keys. So what FEM simulations do, they solve equations governing physical laws. In our instance, we're interested in Maxwell's equation. So what it does is it treats these problems as sort of time independent. So that implies that you're more or less in a non-transient steady state situation where it's used and it's best used where essentially your time and space variables are separable. So what you do is essentially have geometric regions which are independently defined by a given mesh element. And what you can think of a mesh is like, if you've ever, you probably have seen this before, you can almost think of it as like a screen door. So you take the screen off of the door and you wrap it around some material. Along the grids of this screen door, of the screen, if you will, these PDs are solved within each element. So we use COMSOL FEM to find our eigenmodes, or sort of standing waves in our resonators, so that we can get our effective index function of frequency. Why would we want them? I'll tell you what. First, I'm sorry, again, I have to give you a jargon term, but this was the paper I was talking about. So it's Fuji, Shun, and Takasumi, dispersion engineering and measurement of Western gallery modes for carrier frequency cone generation. I strongly encourage this paper, especially for understanding this slide, or just understanding the game of, dispersion engineered microresonators for broadband light generation. This is an excellent paper. But anyways, so what is integrated dispersion? So integrated dispersion, we're following the literature here, and we're sort of expressing it as a function of the modal frequencies of the microwave, the modal resonant frequencies, actually. So mu here represents the longitudinal modal index. D1 mu represents the FSR, free spectral range of the microresonator, where the free spectral range sort of sets an equidistant grid of moments of frequency. And what the integrated dispersion really does is, as you can see, it sort of quantifies the walk-off from this equidistant grid. And so this walk off from the equidistant grid becomes very important for us tailoring integrated dispersion to meet our phase and frequency matching conditions, such that we can have Roy mixing in our silicon nitride microresonators. So how do you tune this walk off? Well, this walk off from this FSR, these high order dispersive terms strongly depend upon your index of refraction, of course, right? Dispersion is related to the index of refraction. So there's 2 degrees of freedom, 2 knobs you have to turn with this. One is choice of material. We're kind of already stuck there. We picked silicon nitride. So that's that. And as you can see, the bulk index is what I'm showing you of silicon nitride. It's not flat. It's pretty curvy. It's dispersive. It's dispersive. So I just in case you didn't know, the dispersion essentially is the curvature of the index of refraction as a function of frequency. And so what's the other degree of freedom? Well, if we want to tune it another way, we can do it by selective choice in geometry. By playing with the ring width and ring height, we can tune our effective index to get even more dispersion, which is exactly what we do. So for a given geometry, we extract the effective index, we get the modal frequency positions, and we can feed that into our integrated dispersion, and we get our nice D intel. So this sort of, so what you have here is a sort of quadratic terms that cause the integrated dispersion to kick up. That's a higher order dispersion term in your D2. And then you also want higher order dispersion as in D3 to sort of cause you to get these cubic terms that cause you to kind of go back down. Whereas you have this sort of zero quality. Well, and that's very important to have this sort of curvy feature of integrated dispersion to support for mixing your microrings, or moreover, in our game here, to actually have spectral translation possible. So through your design of your integrated dispersion, you can meet your phase and frequency matching conditions to identify modes of spectral translation. And the way you tune this integrated dispersion, as I mentioned, choice of material and through choice of geometry. That's why we're varying the ring width and also the ring radius. Okay. So for that same integrated dispersion, I'll show you our visual trick that we use to identify modes of spectral translation. A paper I really recommend for understanding this a little bit better if you're interested. It's a paper by Jen Black. It's optical parametric oscillation and photonic crystal ring resonators. I think they were also using silicon nitride there, but they might have been using tantalum. Anyways, so we form our conservative equation through our integrated dispersion, which is what I'm showing you right here. And so to phase match, we require that the signal be equal and opposite to the Eidler mode. And to sort of frequency match, we impose this antisymmetric condition on the dn of mu signal and dn of minus mu signal. So what does that mean? So for modes that allow for spectral translation or can achieve full wave mixing, it requires that from the pump mode, the Eidler and signal modes must be equidistant from the pump, but they also must be equal and opposite. So if they're equidistant from the pump and they're equal and opposite, you can satisfy phase and frequency matching conditions that conserve energy and momentum and allow for full wave mixing in your microring that we use for our spectral translation. So this is our visual script for identifying modes of spectral translation. And so how do we find new signal? Well, we expand to the 7th order of our integrated dispersion. The odd order terms are naturally antisymmetric, so they just drop out, and you solve for mu signal. And once you solve for mu signal, you know mu Eidler. Great. So this engineering integrated dispersion via ring width. So this is the results of our sort of a finite element model. So what I'm showing you here is a ring radius of 225 microns, pumping at 940 nanometers. So in the orange, I'm just showing you, of course, it's going to be flat because it's your pump wavelength as a function of ring width. Your pump wavelength is not going to change with ring width. We fixed it at 940 here. But what I'm showing you here is your sort of how your Eidler and signal modes change with your choice of ring width. And so as you can see, when you change the ring width, You've changed you modified the effective index of refraction. That means you've gotten a different integrated dispersion, which means that you have a different mode of spectral translation. So what the ring width allows you to do is sort of finely tune your signal either frequencies. And these are great because, as you can see here, we can produce signal frequencies anywhere between 800 nanometers to roughly about 720 nanometers. And we have either signals that are anywhere between 1100 nanometers to about 1300 nanometers. So it's in the telecom. So this is our sort of fine tuning of our signal wavelength, or our either wavelength, also through our choice of ring width. But we have other knobs we can turn. We can also change the ring radii. So here, what I'm showing you here is a fixed ring width. I'm showing you two different ring radii, essentially the signal photon frequency of the different ring radii as a function of pump wavelength. So in the blue is your ring radius of 22.5 microns, and in your magenta is a ring radius of 225 microns. And we're changing the pump wavelength. You might be asking yourself, Ameen, you told me, oh, I can only adjust the dispersion through geometry and choice of material. So what are you doing? I'm changing the pump wavelength to adjust the dispersion.
Where's the big? I thought 9:30 yesterday. I will deliver it today. I will. The deadline is Monday, when you need to work on it. Okay. So I presume there is going to be less problems with maintenance and all, because it's necessary to work. So I will deliver.
Right, okay. Okay. So you can also tune your dispersion by playing with your pump wavelength, actually. So that's another degree of freedom we have here, is sort of tuning our pump wavelength to adjust your dispersion. As you can see here, relative to the ring width, the ring radius offers the sort of coarse control of your signal frequency. So it's a coarse control of your integrated dispersion. So that's the knobs. So the last part of my talk, and what Chris was interested in, efficient coupling. So I'll go again with some more jargon terms. Quality factor, it's the ratio of energy stored to the energy dissipated. The intrinsic quality factor, it reflects the intrinsic losses within the system. So you could think of this as the ring resonator without a coupler. And if we wanted to reflect the losses of the system due to coupling, well, you would just consider the losses of the system with the ring resonator and the coupling. So we define our loaded quality factor, or effective quality factor, which is almost like a capacitance equation or a resistance equation, if you will. Why do we care about it? Well, I'll give you an analogy. We want to be critically coupled at very particular wavelengths. What does it mean to be critically coupled? So just to give you the sort of expression, it essentially means your intrinsic losses are matched by your intrinsic losses. So it's very similar to impedance matching in the sense that when you match your impedance at one side of the circuit to the other, from the source to the load, you're maximizing the power transfer of the circuit. So what we want to do is essentially we're generating, these photons that are spectrally disparate. They're at different wavelengths. So that's great, but we generate them in the microresonator. You look through all that trouble of generating these especially disparate photons in the microresonator. We want to be able to outcouple them. To outcouple them efficiently means that you essentially have to be critically coupled at those wavelengths. It's very crucial for efficient forwardness. So how do we design our couplers? We use finite differencing time domain, or FDTD. We use ANSYS numerical. It's a 3D FDTD solver. And it's very similar to FEM in the sense that although it's not steady state, it is time dependent here. You have transients, but it's similar in the sense that it allows us to solve Maxwell's equations for complex geometries. So we can use these FDTD simulations to optimize the design of our microresonators by determining wavelengths that are interesting, that we need to be critically coupled. So works off of the Yi algorithm. I didn't put the citation here, but the original paper, I think, is from the 1960s. I just went back and read it myself. It's actually quite interesting. But I'll give you my sort of sales pitch on how it works. So it takes Maxwell's equations, which is a continuous set of partial differential equations, and it takes these continuous functions and it turns them into discrete values at specific points. So how does it discretize Maxwell's equations? So you go from a continuous set of differential equations to a set of finite difference equations. Well, this discretization is achieved by solving Maxwell's equations on a staggered rectangular grid, or E cell, which you can see here. So it's very similar to what I helped you guys out through with the FEM simulation, in the sense that you take some complex geometry, you wrap it around with this sort of screen, and you solve Maxwell's equations at each one of these rectangular grids. As you can see clearly here on the bottom right, I'm showing you essentially a polycoupled microresonator wrapped around some grid. And so the FTT region forms a uniform mesh of gauge cells or E cells, excuse me, and it calculates simulation quantities. So that's how we extract our critical coupling using FTT. So I place monitors, the monitor can power in the ring, in the coupling region, and at the outcoupled coupler. So I send in a fundamental T source. That's what these microphones are designed for. I run the simulation, and I use the data from the simulation to calculate our quality coupling factor, or coupling quality factor, as a function of wavelength from the simulation data. Okay. So you have point coupled microresonators. So what I'm showing you here, to be a point coupled microresonator means you got a straight waveguide. We call it point coupler, or point coupled, because there's only one point where the bus waveguide is closest to the microresonator. And you sort of get this monotonic trend with extrinsic or Q coupling as a function of wavelength. So if we were critically coupled, that means that QC would be about 1 million, which I show you with this sort of line here, this horizontal line. And it's fine, but the problem here is that you're only critically coupled at one wavelength. And the issue with that is ideally, you want to be critically coupled at multiple wavelengths. You want to be critically coupled at the pump and at the signal on either frequencies. So you want to be critically coupled at, let's say, 1064 nanometers. You also want to be critically coupled at 800 nanometers, also at about 1100 nanometers. So that's a bit challenging. But the way we do it, polycoupled resonators. So rather than having a polycoupled resonator, you have this sort of polycoupled resonator, which is an arc, and allows you to be sort of close to the ring at multiple points, which gives you this very interesting, almost like resonant-esque quality. QC as a function of wavelength trend. And as you can clearly see here, so what I'm showing you in these different colors here, this different arc lengths of the coupler. So anywhere between 15 micron to 20 micron. Again, this sort of dashed line here is your line of critical coupling. As you can see here, when you have this polycoupled microresonator, you can be critically coupled at multiple wavelengths, which would be useful for us to efficiently use our microresonator for spectral fibrillation. In my advisor Terry has a very interesting paper on polycoupled microresonators. I recommend you guys read it. Anyways, so this is my conclusion. These results enable our group to fabricate silicon nitride microresonators capable of connecting visible quantum emissions to telecom wavelengths. Currently, we're testing our devices to investigate the reliability of our simulation results and testing our opioid efficiency. It's probably my favorite slide. Maybe I should show this. Well, if you're
Go ahead.
It's my group.
Yeah, go ahead.
Okay, yeah. So this really is my favorite slide. That's my advisor, Terry Drake. These are all of us who are under her advisement. Lava Rugardi is graduating. That's me. This is Brandon Stone. It's Gabriel Colacion. This is our newest lab member, Angie. This is just us having fun. I learned a lot from these guys. It's really fun working with them. They're both extremely intelligent, very kind, and we have a lot of fun with these guys. So that's all, guys.
All right, thanks for great presentation.
Thank you.
So let us open the discussion.
Yeah.
Do we have any questions from the audience? Maybe I will have a question in regards to quantum photonic computer implementation. So by your knowledge, which techniques how would you design quantum gates on a photonic computer, and how would associate this quantum gates with your microstructures that you model and that you produce somehow?
It's a great question. So as far as quantum computing on a photonic circuit, as you're well aware, it's much more complicated than using, like, let's say, like your solid state based systems, but there's sort of 5 things you need to tackle. One of the first things is sources. The other thing you need to tackle is detectors. The other thing you'll need to tackle is algorithms, putting together a sort of, how do you say, a composite system that sort of uses all these things together. So the first challenge is really trying to address here is sources. So trying to have sources on a chip, as you can see, because of the wavelength that they emitted, is a challenge because they're lossy. It's a lossy wavelength. So the challenge we're trying to address for that end game is sort of making them less lossy through spectral translation. So taking them from 500 to 800 nanometers to the telecom wavelengths will be less lossy. As far as the long game for design and quantum computers, I think you'll have to ask someone much more smarter than me. I don't have a great answer for that. But it's not something you can just solve at once. It's a sort of stepwise process. So we're just trying to address the problem of sources of the chip scale.
All right. Do we have any other question? All right. So if not, let us thank the speaker, and let us continue this sequence of presentations. Thank you.
Yeah, Poland.
Thank you.